Hello, I'm Hyunsu, a sixth year graduate student at the University of Texas at Austin, working with Michael Boyle and Colchin. Today, I'll be discussing some of the most important small-scale tests and problems of ΛCDM and their current status and how I approach them. Before I get started, I would like to thank the organizers for giving me this opportunity to share my work. To give a sense of the scales I'm interested in, I'd like to start with the phase diagram of dark matter structure that shows the wave number k and its relation with time or the redshift. The left side of this figure is the density fluctuation or the large-scale structure regime, and the right side of it is the small-scale halo regime. In the linear large-scale regime, ΛCDM is well tested with a few potential tensions, but nothing that points away from the basic picture of cold dark matter plus dark energy. And we know that dark matter must be cold at these scales. In the non-linear small-scale regime, the model is not well tested, and there are a variety of persisting and new discrepancies between theoretical predictions and observations. And through these problems, we have the potential to test the nature of dark matter and look for deviations from the cold, collisionless picture. In this small-scale regime, there are many ongoing efforts that aim to test the CDM paradigm and to discover dark matter substructures. And here I'll quickly go over some of the most promising efforts. The first example is by studying dark matter halo interactions with thin stellar streams from disrupted globular clusters. Here I'm showing the result from Bonazza et al. 2019 that showed the structural characteristics such as the gaps and spurs in the observed GD1 stellar stream can be reproduced in a simulated model that models a thin stellar stream undergoing interactions with dark matter subhalos passing by. And now that Gaia has given us close to 100 observation stellar streams around the Milky Way, studying subhalo stream interactions is becoming a promising avenue to detect dark matter subhalos. Another example is studying the perturbations that dark subhalos within a lens galaxy can leave on lensed images of background light sources, such as galaxies and quasars. Within the ΛCDM, galaxies and their dark matter halos are predicted to host an abundance of subhalos, and studying their gravitational effects is another promising way to detect dark matter subhalos. And the final example of small-scale tests is to compare the observed population of satellite galaxies around the Milky Way with the predicted population of dark matter subhalos these galaxies can form out of. All of these methods can serve as crucial discriminators among dark matter models because they will tell us the statistical properties of dark matter subhalos that vary depending on the dark matter model. And all of these avenues, however, require that we accurately understand the distribution of dark matter at the low mass scales. For example, thin streams and lensing anomalies are thought to be sensitive to low mass subhalos, and in order to have correct estimates of the frequencies of subhalo stream interactions or perturbations in lens images, we need an accurate understanding of the statistical properties of dark matter subhalos. Also, our predictions for the satellite galaxy distribution are directly dependent on these statistical properties. This means that we need to understand the effects of galaxy formation on the dark matter distribution and vice versa, so that we understand the statistical properties of dark matter substructures that are relevant for these searches. We also then need to make accurate comparisons between observations and simulations and simulations are the primary tool we use to study dark matter subhalos. To do that, we need to make sure we are accurately characterizing small-scale structures deep within larger-scale structures. But there is a problem with that. Many of the tools we have are calibrated for different systems and often large volume systems. So we need to make sure that the theoretical models are as complete as possible and tuned to the specific problems at hand, which means that we need better tools for tracking substructure in simulations. So what actually are the problems with the traditional way we study subhalos? When we're done running simulations, we then identify at each simulation snapshot halos and subhalos using a halo finder. We then use a merge tree tool to create links across snapshots, attempting to gather the evolution history for these halos and subhalos. And here we immediately see a potential problem, which is having to accurately identify substructure deep within a larger scale structure. In these deep central regions, the gravitational potential of the host system tidally strips particles away from the subhalos. And also, these regions already have a dense background of host particles, which means it is very challenging to identify and track subhalos in such regions. To show what this challenge looks like when analyzing real simulation data, I show here the evolution of an example subhalo from the Phat ELVIS project. Phat ELVIS project has a suite of cosmological simulations, and here the black dashed line shows the evolution of the distance of the subhalo from the host center according to a widely used merge tree code, consistent trees. The subhalo infalls into the host halo about 11 gigayears ago, crossing the virial radius of the host halo, whose evolution is shown as a dotted line. This subhalo then completes two very close pericentric passages before it disrupts at 9 gigayears in lookback time, according to consistent trees. We can also track its mass evolution by overplotting its Vmax, the maximum circular velocity, which can be read off of the axis on the right. Here and throughout this talk, I use velocities such as Vmax or Vpeak to characterize the subhalo mass instead of using the actual mass. And I do that because the mass of the subhalo depends on how we define the boundary of the subhalo, but these velocity characteristics do not. Also, these quantities are what we observe in observations of galaxies, not their masses. So going back to this subhalo, just prior to the infall, this subhalo attains its peak mass or Vpeak of around 35 kilometers per second. And as it orbits within the host halo, it experiences mass loss due to the host system, eventually disrupting when it has a Vmax of about 20 kilometers per second. That corresponds to about 10 to the 9 solar masses. What's puzzling about it is that this mass is orders of magnitude above the halo mass resolution of the simulation, and that the subhalo still has over 30,000 particles when it disrupts. We then must ask, is it actually disrupted, or is it just lost by consistent trees? And we can answer that by tracking the same subhalo with its particles from the infall snapshot. When we do that, we see that this subhalo actually survives 9 gigayears longer than it does in consistent trees, all the way down to redshift 0, completing 6 additional pericentric passages before becoming a subhalo with Vmax of around 5 kilometers per second. This is just one of many examples of consistent trees losing subhalos prematurely, and there also are several other tracking problems associated with these traditional merger tree tools that I won't discuss here. But the fact that there are many problems and that they happen frequently is a challenge that must be addressed if we want to make accurate predictions for subhalo abundance. To do that, I have developed a subhalo tracking package called Bloodhound, and I plan to make it public. Bloodhound approaches subhalo tracking with a straightforward philosophy. While identifying subhalos is hard, especially if they're embedded deep within the host, identifying isolated halos before they become subhalos is relatively straightforward. Once infalling halos are identified, we can track their particles forward in simulation time. And by directly tracking particles, Bloodhound never has to play the guessing game that traditional merger trees need to play when attempting to connect progenitors to descendant halos. And now that I've introduced Bloodhound and an example of how it improves subhalo tracking, I want to discuss the improvements in a more statistical way. Here I am showing the median distribution of V disrupt, which is the subhalo mass or Vmax and subhalos disruption from all 12 simulations in our Phat ELVIS project. The dashed line shows the distribution from the standard model, consistent trees, and tells us that a typical disrupted subhalo disrupts when its Vmax is around 10 kilometers per second, with a large number of subhalos disrupting at higher masses. And that is a big problem, considering that the halo mass resolution of the simulation is much lower at 4.5 kilometers per second, meaning essentially all subhalos are disrupted or lost before they reach the resolution limit. And another problem we learned from this figure is that there is a large number of subhalos disrupting at very high masses, with some of them being as massive as Milky Way's most massive satellite galaxy, the Large Magellanic Cloud. The same distribution of disruption mass from Bloodhound sees a significant shift towards smaller masses, with the peak of the distribution telling us that a typical disrupted subhalo now disrupts near the mass resolution of the simulation, and also the most massive disrupted subhalos disrupt at much smaller and more reasonable masses. This result comes from the fact that Bloodhound can track subhalos for much longer time periods than consistent trees can, which tends to lose a lot of subhalos right at the pericenter, not because they're truly disrupted, but because they become embedded within the central regions of the host halo momentarily and become very difficult to find. The faithful tracking made available by Bloodhound means that we obtain significant corrections to existing predictions just by tracking subhalos better. Here I show the median V peak cumulative distributions with the consistent trees result showing in dashed lines and Bloodhound result in solid lines. The black lines are for our dark matter only simulations, and purple lines are for the same simulations with embedded galaxy potentials that resemble a more realistic Milky Way environment. And in the bottom panel, I show the ratios of the distributions from the two methods to compare their performances. And it's obvious that Bloodhound outperforms consistent trees and finds more than twice as many surviving subhalos with V peak greater than 20 kilometers per second within 50 kiloparsecs from the center of the host halo. And we see that in the disk run, we find significantly more surviving subhalos down to 10 kilometers per second, which is where the Bloodhound analysis stops. The radial distribution of subhalos also experiences a significant change with Bloodhound. Previously, with consistent trees, subhalos with V-peak above 17 kilometers per second were thought to be depleted within 50 kiloparsecs, but Bloodhound finds them as close as 30 kiloparsecs, and this is very significant because in observations we have observed faint satellite galaxies in these central regions, and now we are able to predict the existence of subhalos that are massive enough to form galaxies in these regions. And we also see that Bloodhound predicts twice as many subhalos that are above the atomic cooling limit of 10,000 Kelvin, which corresponds to the V-peak of 17 kilometers per second and all the way out to 100 kiloparsecs. And this may hint that the recent too many satellites problem is not a problem after all. So far, I have shared some of my preliminary results, and my next steps are to extend the Bloodhound analysis to all subhalos in the Phat ELVIS simulations. With that, I'll be able to probe really low mass subhalos that are thought to be attractive targets for many of the astrophysical dark matter discovery efforts I mentioned earlier. Equipped with Bloodhound's faithful subhalo tracking, I am working on studying the formation mechanisms for ultra-diffuse galaxies in the fire simulations, and also with the correct predictions for the abundance of dark matter subhalos, I am working on addressing the ultra-faint satellite galaxy completeness and compare the observations from the upcoming LSST survey, and revisit the satellite distribution problems of the Milky Way. Through that, we may be able to extend our knowledge of galaxy formation for low-mass galaxies that form via molecular cooling instead of the canonical atomic cooling mechanism. On the dark side, I'll revise existing predictions for subhalo stream interactions and subhalo lensing perturbations. And finally, I'll apply Bloodhound to simulations of alternative dark matter models, such as self-interacting dark matter. This concludes my talk, and thank you.